Okay, let's talk about compound events today. So what is a compound event? It is an event made up of two events. And we join compound events, just kind of like sentences in English, with an and or an or. Okay, so and or are going to come up and play. We need to be able to have a strategy when we see both of those words. So we're going to go by example and study that. Independent events is very important to know what that means. Independent, just like in English, the word independent, they're kind of separated, right? Independent people aren't affected by others, right? They're confident. So independent events are events that do not affect how the other, it's typically a pair of events. So one doesn't affect how the other occurs. Okay. And if you have independent events, then we have a really nice formula for and. And that formula is the probability of A times the probability of B. And I don't think we're going to see this on the first page, but we're going to see it later, because none of these on the first page are independent events. They're all just a single event, at least with the first one. So we'll go through that, but we're going to definitely use this later. So just kind of hold on to this. Okay. And mutually exclusive, if I had to say that in one word that we know, it would be distinct. So almost separated from one another. They cannot happen at the same time. Okay, so it's kind of like asking a group of folks like which sport they like, baseball or hockey, and none of them say baseball and hockey together. They're all like one or the other. Right? That's mutually exclusive. And visually it looks like this. When you have groups that have no intersection. Typically a Venn diagram looks like this, right? Mutually exclusive says, hey, let's look at them and have them be completely separate. Okay? And that will affect how we do the OR calculation. Okay? So, first, we're selecting one marble from a collection of colors. What's the probability that one marble is red and blue? 0. I mean, that's not possible. You can't pick one marble and have it be both colors. That's not how the problem was presented. So what we would say for this is the probability of red and blue happening at the same time is 0. And that's what mutually exclusive means mathematically. It means that the probability that both of them happening is 0. So this means that red and blue, and also yellow, put a little circle for yellow, they're all distinct. They don't touch. Okay? So when that's the case, if you want to find the probability of red or blue, all you need to do is just add up. Oops, it's too big. You need to add up the probability you're in here and the probability that you're in here. Only for mutually exclusive can we use that formula. Or does not mean like plus. It means that for us right now, since these events do not overlap, you can't do both of them at the same time, the probability is the sum of those two, which would be 14 out of 30 plus 10 out of 30, which we'll just say is 24 out of 30. When there's overlap, the rule changes a little bit, this rule. So we're going to track that as we go and see if we can find any examples. that do have overlap. In fact, we have one right here. So we have someone rolling a 20-sided die once. Find the probability for each. So the probability of rolling an odd and a multiple of 5. We could honestly just list for both A and B here, we could just list the numbers that are successes for us. So why not just write out all the numbers and circle them? Could be fun. 11, 12, 13, 14, 15, 16, 17. So with problems where like the numbers are small enough, this one's kind of borderline with 20, but you can always list the possible things and just kind of circle the ones that are successes. So if we want a multiple of 5, we're only really narrowed down to these 4, right? But they have to be odd as well. So the only of those that are odd are just these 2. So the chance of that happening is 2 out of 20 numbers. Okay. Now, let's copy and paste those. So that was and. So and always means both. It means that in English too. So or, though, means one or the other or both. So it could be odd, it could be multiple of 5, and it could be both, and it would still be considered a success. So anything that's an odd number is going to qualify us. So I'm going to highlight all the odd numbers. Okay. And anything that's a multiple of 5 works too. So we have to add, 5 is already counted, and so is 15. But we need to make sure 10 and 20 are included in our calculation as well. And it looks like this would be the probability. But what's interesting is we could get to that by, remember before up here we added? You can still add these together. But if you notice, when we were doing the multiples of 5, we said, hey, we already, you see how I've double counted 15 and 5, right? We don't want to count those twice because, we only had 20 events. We can't double count anything. 20 outcomes, I mean. So when you add them together, you have to subtract any duplicates. So the duplicates would be the ones that are in both events. So this would turn out being, hey, you have a half chance of getting odd, a 4 out of 20 chance of being a multiple of 5, but there's 2 numbers that were double counted, 5 and 15, so we have to subtract those, okay? And this is huge. I mean, this is one of the toughest parts of these notes, and this has its own name, and it's called the addition rule. The addition rule says that with or, you can always do add the 2 together, but subtract any overlap. Because we saw in those 15 and 5 were in both. 15 and 5 were in both groups. So if you just added them together, you would be double counting them. So you have to subtract them. This all checks out visually too with these Venn diagrams. So this is going to be the probability. Oops. Or I'm just going to go ahead and show you what and or look like on these. Together, and would be everything within the 2 circles, just a nice clean shading in, and oh, I'm so sorry. This is or, because it includes everything, right? And would only be the intersection. So what's interesting is if you take A and B and you add those together, you would get, let's do this in So here's us adding A. So I'm right here. We just did this. And then I'm going to add B. And if you see the red and the blue make it a little purple in the middle, but A or B right here is just an even shading. There's no duplicate. So we have to actually subtract A intersection to really get A or B like that, because we've double counted the middle. I'll leave it at that. But this formula is really crucial. I'm going to give it to you on the test. It's given to you on the air test. It's the only probability rule that's given. So you will have that. Okay. So let's practice it here so we know how to use it. So we got tiles in a bag, 4 colors, and each color has a tile from 1 to 10. So how many tiles are in there? 40. 10 black, 10 pink, 10 blue, and 10 red. So what's the probability we pick a tile that's blue or a 10? The probability that it's blue would be 10 out of the 40 tiles, a quarter of them. And the probability that you have a 10 could be, it could be the black 10, the pink 10, the blue 10, or the red 10. So the addition rule says the probability of blue or 10 should be the probability of blue plus the probability of 10 minus the probability of blue and 10. Oh, sorry, that should be a 4. And what's the probability we pick a tile that's blue and a 10? Well, there's only 10 blue tiles, and only one of them is a 10. So we know that this is 1 out of 40. So there's a 13 out of 14 chance. Because if we just were to add these together, we would be double counting the tile that's blue and a 10. You see? So we only count stuff once. So us subtracting means that we are removing the duplicate. Okay. Same thing here. So when you see or, the answer should be the addition rule. Add them up and subtract when it's both. So this would be 10 out of 40. Bigger than 5 is half the tiles. Half of them are less than or equal to 5. So this would be 20 over 40. And the red tiles, there's 10 of them, and there's only 5 of them that are bigger than 5. So the answer here is 25 out of 40. Okay. All right, now time for some Venn diagrams. I think these are really fun, much more fun than the addition rule. But it's actually using the same math. So I'll show you once. But okay, so student athletes may participate in only one sport. That's setting up mutually exclusive. Like, so when I draw my Venn diagram for this, you either play baseball, you play lacrosse, or you do none of them. There is no overlap because they only can pick one, right? So I always just go in order and say this is A and this is B. And they're telling me that 28% are in baseball and 24% are in lacrosse. So that's that. Now, there's 100% in total. So the 28% and the 24% do not add up to 100. So there's actually, it adds to 52. So 48% is actually hanging out outside of those bubbles. Okay, so those are the people that played in neither sport. which seems pretty representative, right? Like if you're out of school, not everyone's going to play those two sports. You know, there's going to be some that don't. So the question is, what's the probability that if you pick a random student that they play either basketball, wait, oh, this should say baseball, or lacrosse. So that would be simply the probability of A plus the probability of B. Because those events have no overlap, we don't need to worry about double counting anyone. We can just add the groups together. Okay. So note the probability of A and B equals 0. And addition rule, if I write it out really fast for us, normally subtracts that, right? But in this case, this is 0. There's no overlap. So that's why the formula is just to add them. Okay, so addition rule works even for an example where there's no overlap. It's just that the probability of being in the overlap is 0. All right, let's look at 2 more Venn diagrams, and then we'll do just a tad more about independent and dependent. So we got school keys. We got 80 of them, and they're inside of this. We call it the universe for some reason, but the universe is all 80 of these keys, and some of them open classroom doors, A, and some of them open the teacher's lounge, B. Okay, you would hope that all of the teachers' keys open the teacher's lounge, but in this case, that's actually not true. Oh, and look, they're giving us the third. They say 30 open classroom doors and the teacher's lounge. So that's A and B, or the intersection. So there are some keys that do both. You would think all of them would do both, but that's not the case here with the keys. So maybe some of these keys don't go to teachers who can do both. But we got A and B. I always start with the intersection when I'm filling this out. So 30 are inside of here. Okay. A has 60. So this, inside of this A bubble, should be a total of 60. Does not mean that this is 60, because then you'd have 90. You see? So you actually have to do a little subtraction and figure out, okay, if A is going to be 60, it's got to be 30 where it's just A, and 30 in the overlap. And same thing for B. 40 keys open the teacher's lounge, B, but 30 do both. So there's only room for 10. Okay. So what's the probability that a key opens no doors? Well, we know the universe, all of our keys is 80, but how many are in here? How many are in that blue part? There's only 70. You see? So 10 fall in the outside. There's normally always something that's on the outside of the Venn diagram. Okay, something that just doesn't belong. And there's 10 keys that do neither. Okay. We got pet owners this time. We have 150. And we have some with cats, some with dogs, some with both. So I always look at both first. And we'll call dogs A. The event that you have a dog is A. The event that you have a cat is B. Um, 31 lie in here. And for A, for dogs, there's 88. So it's going to be something, so inside of this bubble, whatever's here, you need to add it to 31 to get 88. So 57. Okay, so you don't just slap 88 in there, because A is inside the whole thing and it contains two parts. It's either the part that's just A or the part that also has B. So if there's, in the B group, if there's 52, then that means there's 21 here. Okay? And if you do a little bit of calculating, you'll see that there's 41 left over. If you add up all four of those numbers, you should get 150. What's the probability that a randomly selected pet owner owns a cat or a dog? That would be anyone that's in this shape, right? Having a dog qualifies you, having a cat qualifies you, but even if you have both, you still qualify for cat or dog, right? It's still a yes. You know, you ask someone, hey, do you have a cat or a dog? Yeah, I do. I have both. It's fair. We tally that. That counts. So the answer to this would be 57 plus 31 plus 21, which is 109 out of 150. So this is the probability of A or B, which we could calculate with the addition rule too. The Venn diagram is just another way to look at the addition rule. All right. So the last part is just these quick questions on independent versus dependent. So now we're looking at successive events. We use this to describe events occurring one after another. And they could be independent or dependent. We'll use that as our abbreviation. Now, if they're successive events, then the and is, which is typically what happens here. We don't use or in this setup. It's always and. But the truth is it's either going to be, so this from the very beginning, we talked about if it's independent, you have this formula. So here's where we're going to use it. And if it's dependent, we actually follow the next rule, which looks really scary, and I don't want you to worry about it right now. But it's just saying that it's, if you have dependent events, it's going to be the probability of A times the probability of B, given that A happens, because A has an effect. For dependent, A affects B. Right, one event happening affects the other. So we get this kind of weird probability that's adjusted for us knowing that A already happened. But you can see with the formulas that if it's independent, that entire chunk becomes probability of B. Okay, so we'll go back to that box at the end and kind of restate what we learned after doing these examples. So Isabella is rolling a 6-sided die and then selecting a letter tile from a bag with the tile's memory in it. So are these independent? Well, the die and picking a tile have nothing to do with each other. One's not going to affect the other. So these are independent. And what's the probability that they both happen? Well, it's the probability you draw an even times the probability you pick an M. So 3 out of 6 times 2 out of 6 is 6 out of 36. So independent events just multiply. Okay. And this is true like with more basic examples too, with like heads and tails. Like what's the probability the first coin is tails and the next coin is heads? It would be 1/2 times 1/2. Okay, because the first coin doesn't affect the second coin. Okay, so we have Sally here who has a deck of cards and she picks one but does not replace it. She takes it out of the deck and then she picks another one. So the first draw, like if you pick an ace, then the rest of the cards in the deck, you're going to have less of a chance of picking an ace because it's gone. So these are dependent events because one of them depends on the other. Okay, so what's the probability that you select the ace of clubs? There's only one of those, so that's 1 out of 52 times the probability of you picking a heart. Okay, we don't have 52 cards anymore. We have 51. You see? So that's where the dependent part comes in. When you have dependent events, you have to affect the denominator because typically you're taking something out, right? And how many of those cards left are hearts? Well, the ace of clubs was not a heart, so we still have all 13 of our hearts, meaning that I think if you simplify this down, you get 1 out of 204. Okay, so this here, this more complicated adjusted event is what this is up there in blue. Okay, it's the probability that you draw a heart given that you did an ace of clubs. And sometimes the probability is still, because you would expect the probability to draw a heart to be 1/4. So that's the probability of B, unaffected, independent, right? But this weird little thing, that's the probability that you draw a heart given that you drew the ace of clubs. And we're going to get into this in the very last probability section, this given idea. Okay. And the next section. So let's finish this up. So you got some marbles. Steven picks a marble without replacing it and then picks another one. So he just takes a marble and takes it out and then picks another one. Well, that's not, if you replaced it, it'd be different. But he took it out. So this is a dependent. The first pole affects the second. And what's the probability that he selects a blue? And then the probability that he selects a yellow, given that the blue was drawn. So it looks like there are 5 out of 20 marbles that are blue, and there's 9 out of 20 that are yellow. But remember, he took one out. So we don't have 20. We have 19. Okay? So dependent events shift the denominator. So I'm not really in the mood to simplify this, so we'll leave it like that. Okay? So these are, again, dependent events. So Miss Smith's class has 13 boys and 14 girls. 17 girls. And then she calls on a random student. And then she calls on a different random student. So whoever was picked to answer the first question is out of the running to pick the second one. And when that happens, that's dependent. Okay? So what's the probability that Miss Smith calls on a girl? The first event is always like straight shooting. Calling on a girl is 17 out of 30 chance. And what's the probability that she calls on another girl? Well, after that event, after event A, there is one less girl. So there's only 16 girls to pick from, and there's only 29 people to pick from in the whole class. All right, so that's it. There's a lot of homework to do. I highlighted the ones that are that you really should focus on and do. I think you should do all of them and check the key. That'll help you the most for the test that's coming up.